In this video, I'm going to teach you about the VSEPR theory. But before we get started on that, I want to remind you of where we're going with this. We are talking about covalent molecular compounds, or molecular covalent compounds. These are the ones that, if they ever form a solid, they're going to do so from intermolecular forces, bringing all the particles together, clumping them up. So what we begin doing in this unit is drawing our Lewis structures for these covalent molecular compounds. And then our ultimate goal is to figure out what intermolecular forces these are going to have. But before we can do that, we have to take that Lewis structure and then we have to assign a shape, a geometry to that structure in order to see if it's polar or nonpolar. Once we know it's polar or nonpolar, then we can start hypothesizing about the IMFs that are present. The bonding theory that allows us or tells us how to do this, going from Lewis structure to geometry, is VSEPR. Now, it's an older theory, it's been around for decades, but it works pretty well for figuring out geometries. VSEPR, as you can see on the screen, stands for valence shell electron pair repulsion. And the main idea of this is that electrons repel. When you put electrons around a central atom, like we've been doing on our Lewis structure, those are called domains, and they are going to repel each other. That means that when you build the geometries, these electron pairs are going to get as far away from each other as possible. That's where the geometries come from. They'll do it in as many dimensions as are needed. One-dimensional, two-dimensional, or even three-dimensional. But the main idea is that those domains repel each other, and that sets the geometry. The first step in determining geometry is to determine the electron domain geometry. Now, this is the term I choose to use the most. Other terms you may hear in a textbook or from other teachers or students at other schools will be electronic geometry or base geometry, and I'm sure there are others, but I call it electron domain geometry. On the screen here, you see 5. There are only 5 of these that we're going to learn. Now, in full disclosure, these go on and they become way more complicated, but as you get past octahedral, they become increasingly rare. You will see them from time to time, but most of you will never see them ever. It really would require an inorganic chemist to work with ones beyond octahedral, and again, they're rare. So we're going to focus on these 5 this year. We're going to go through each one and kind of play with it using some modeling software here, but I just wanted to show you all 5 at once. Once you get your Lewis structure, your next step is to pick one of these 5 geometries to begin. The next step would be to find the molecular geometry, but your job is to pick one of these 5 first, then evaluate your domains and pick the subset of each of these domains that would give you the molecular geometry. And then the subset is determined by what these domains look like, and I'll talk more about that in the next video. But first, what is a domain? When I use the word electron domain, really what I'm talking about is a region where electrons are around the central atom. They can be single bonds, the shared pairs, or they could be multiple bonds. A double bond is just one domain. It's a rich domain with more electrons in it than normal, but it's still just one area where electrons are found. So you count multiple bonds as one domain. Same with triple, that's just one domain. Lone pairs we've put around the central atom, those also occupy just one space, so those are domains. And then we did see a couple of Lewis structures. I'm thinking of NO, molecule nitrogen monoxide, that has a radical. And so when you have a single electron, that also occupies a domain and determines the geometry. Let's quickly go through each of the 5 domains, and I just want to talk about them each briefly. The first geometry, electron domain geometry that we have is called linear. And that occurs when you have two domains. We can see here one on the left and one on the right. They're shared pairs, which is fine. So they are two domains. If I have two things and I want to get them as far away from each other as possible, you can see here from the model that 180 degrees is as far apart as I can get two things. So that's your linear geometry. It's only one-dimensional. Let's add another shared pair and have three domains. It really doesn't matter if they're shared or not. I'll show you that here momentarily. But if I have three things, they will get a set distance apart. We call this trigonal planar. And the reason we call it trigonal planar is because it makes the shape of a triangle. And it's flat. So it occupies only two dimensions. It's a plane. And the bond angles between each domain are 120 degrees. That's as far as you can get three things apart in a plane, 120 degrees. Now before I go to the next domain, let me just kind of show you that it doesn't matter what the domains are. So here I've put in two lone pairs as my domain, and I have just the singular shared pair. It looks a little funny because lone pairs are bigger and fatter and more repulsive than the shared pairs, but the bond angles are still about the same. They won't be exactly the same, but they are pretty close to the same. Here in this example, you're probably going to see slightly less than 120, and then here this would, across the top between these two, probably a little bit greater than 120. But when you assign geometries, if you had one like this, you count the domains, 1, 2, 3 domains, you're going to assign it trigonal planar electron domain geometry. And then we'll account for the actual shape, the molecular geometry, later. All right, I'm not going to do that for every one of these. I just wanted to show you once that domains all create the same electron domain geometry. All right, so we're back to our trigonal planar. We've had one-dimensional and then two-dimensional, and now let's add a fourth domain, a bonding domain, and look at the shape we get. Most of you might have been expecting a square. You're not going to get a square because if I put them in a square plane, that means the four domains will be 90 degrees apart. It's not bad, but I can do better, and I can do better by going into three dimensions. The way I originally had it oriented, you can see here that we're definitely going into three dimensions. I have atoms or domains on the left and the right in the plane of the screen, and then you can see here I have one pointing right at you, and at the same time there's one pointing back into the monitor. So that is three-dimensional. The bond angles here are all the same. This is a tetrahedron. It's one of the Platonic solids that you may have learned about in geometry. It's one of the most symmetrical shapes we have in nature, one of the half dozen or so that's really, really symmetrical. The bond angles are 109.5. It's by far the strangest bond angle we're going to encounter, but that's just what it is. In one of our activities, you're going to have a chance to build this shape, and students have the most difficult time building this shape because you have to think three-dimensionally. Believe it or not, you're not used to thinking three-dimensionally. You're used to doing three-dimensionally, but not thinking. So when you build something, you have to go into, or you have to train your brain to think three-dimensionally. So one way I tell students to build this molecule, notice that we have a V shape, okay, on the bottom here, a V pointing down. And then on the top, I actually have another V, and that V would be pointing up, but it's pointing up perpendicular to the first V. You see that? So we have a V pointing straight up, and if I rotate that molecule around, we have the V pointing straight down. Not the easiest thing to manipulate here. So either straight down and then straight up at 90 degrees. Okay, so that's the first two, our first three domain geometries. Let's add a single bond here, and let's go to 5 domains, and we get one of our expanded octet geometries. This is trigonal bipyramidal. Let's talk real quickly about why it's called trigonal bipyramidal. That is because if I were to look at this thing, that's the shape I want right there. Looking down the axis here, the central part, the equator if you will, makes the shape of a triangle. And then I have one triangle pointed up, and then I have one triangle pointed down. So that's why it's called bipyramidal. And it's a triangular pyramid, a triangular based pyramid. So trigonal bipyramidal. Another very important thing for you to understand about this shape as we expand the octets is that we have two distinct regions of electrons now, and you need to get used to this terminology. On top and bottom, back up a half a step, think of the purple ball, the central atom here, as Earth. Many of you have had geometry for a lot of years in elementary school, and you know that there's an axis, a north and south pole that runs to the center of the Earth. So this position here in geometry is called the axial position, and those two are at 180 from each other. Around the center, the equator, we call that the equatorial position. This equatorial position in this geometry is really just trigonal planar around the center, and they're 120 degrees apart in this equatorial position. So we have a combination of bond angles in this electron domain geometry. We have the 180 between the axial positions, we have the 120 between the equatorial positions, and then we have 90 degrees between an axial and an equatorial domain. Believe it or not, this shape is still symmetrical. All the electron pulls would cancel. So if you're in this electron domain geometry and all of your terminal atoms are the same, you do have symmetry. Let's add one more and make our last electron shape here. This is called octahedral. Now, like the tetrahedron, the octahedron is named not for the number of atoms, but for the number of faces. If I were to close this in, connect all the dots, if you will, shade it in, I get an octahedron, an 8-faced polyhedron from geometry. Right now, you're in essence kind of looking at the skeleton of the octahedron, what makes it up. You'd have to actually draw it in, fill it in, and see what it looks like, but there's 8 faces. Very similar to trigonal bipyramidal, we have two distinct regions. We have the axial position again, and we have the equatorial position again. This time, the equatorial position is not a triangle, it makes up a square. This is a square plane, and the bond angles are all 90 degrees. And if we take it back up and look at it from the other standpoint, there's 90 degrees between the two planes, or between the two positions as well. So in octahedral, it's another platonic solid, a very, very symmetrical shape in nature, and it is all 90 degrees everywhere. So one little quick thing before we end this video, let's go back to our trigonal planar, since I used it to illustrate the lone pairs and how the geometry would be the same. I should have done so for the multiple bonds. So let me just throw a double bond in here just to prove to you that the presence of that double bond doesn't change the number of domains. It's still 3 domains. They're still about 120 degrees apart, and we still have trigonal planar electron domain. So multiple bonds don't affect anything. One last little bit, I'm going to go back to the original PowerPoint slide, and I'm going to give you a little sneak peek toward hybridization. Hybridization is actually not part of VSEPR, but like I said, this is a sneak peek. We go into the next bonding theory called valence bond theory that will describe hybrid orbitals. Now there's going to be a separate video on that, but for right now, just let me tell you this. Each of the electron domains that we just learned and went through has a very specific hybridization that will always be assigned to that shape. For linear, it will always be SP. Trigonal planar will always be SP2, tetrahedral is always SP3, and then so on. So for memorization purposes, that's all you need to know. As I teach you about hybridization in the upcoming lessons, you'll understand what the S and the P's and the D's mean. But for now, just know that each domain has its own hybridization scheme. All right, so if you have any questions about finding electron domain geometry, be sure to come by and get help.